So, good afternoon, everybody. I hope you are well seated with a good cup of coffee and tea for this webinar of Chemport Connect on biobased, on new biobased polymer applications for high-value markets. My name is Willemien Vele. I work at K&N Consultancy, which is a consultancy company specialized in enabling bio-based and circular business development. And I also work for an organization called Circular Friesland, for which I am a change agent for the Northern Netherlands for bio-based and circular plastics. Circular Friesland is an organization built from companies, knowledge institutes, and municipalities, and we work to accelerate the transition toward the circular economy on several topics: bio-based, biomass, built environment, education, but also plastics, and that's the theme I'm working on. And today I would like to welcome you again for this webinar. We will start with a few speakers quickly, but I first would like to ask you to use the webinar rule set. If you have any questions, please ask them directly via the chat, not via the Q&A. Please state your name and organization, and the person the question is directed to if you have a specific question. And we would also love to hear from you what you would like to learn from this webinar. So we can check back later if we have reached that goal as well. And to start the action on the chat a bit, we have started with a poll. And the question is, and now I need to share the poll. It started. So what is the current share of the bioplastics production capacity compared to the world plastic production capacity? So if you would please, is it A, less than 1%, B, 1 to 5%, or C, more than 5%? To see what the state of your knowledge is of our viewers. Okay, so I see that about almost everybody has started their vote. I'll just leave it running a bit. Everybody has voted. Okay, well, most of you think it's less than 1%, about 53%. 40% thinks it's between 1 and 5, and these people think it's more than 5%. Well, the answer will be presented to you by one of our speakers today, so the answer will follow. These are the results. Okay, so I just wanted to introduce myself a bit more. As I stated, I worked as a change agent for the organization called Circular Friesland. And the past year, I've been mapping the Northern Netherlands ecosystem on circular plastics. And as you can see in this picture, this is a map of the northern part of the Netherlands for the people who don't know the Netherlands that well. We have a few areas, and a lot of companies are working in the fields of plastics. And what I found out is that in the Northern Netherlands, we have several regions with a lot of mechanical recycling in this part of the Friesland part of the Northern Netherlands. We have chemical recycling specialized in depolymerization in the area of Drenthe with the Cure technology. We have chemical recycling in the Groningen part, the harbor part of our country, specialized in more pyrolysis and gasification chemical recycling. We have feedstock coming in through the harbors. We have knowledge institutes like the University of Groningen and NIHL Stenden on polymers, but also on design. We have production industry, so we have a lot of assets in this area, and we are working closely together to actually realize more circular plastics ecosystem. So this map is on the transformation of waste plastics towards new products, but also we have bio-based feedstock developments in the northern parts of the Netherlands. One of the viewers, as I saw, is the company called PAC here in Friesland, which produce biodegradable, which are going to produce biodegradable bio-based polymers, but also Teijin in Delfzijl areas producing bio-based feedstock. And here in the Drenthe Emmen area, we have bio-based processing companies. And so we have a lot of beautiful companies here and a beautiful ecosystem. If you want to know more about this, please contact us after the webinar. And a few speakers of this ecosystem you will hear in the following hour. First, we will start off with Vincent Voet, who's an associate lecturer at the NHL Stenden. Then we will have Jan-Willem Slijkoort, which is a founder at SEORG, which is a clean tech startup. And at the end, we'll have Bart Labrie, CEO of HMP Molding. And afterwards, we have room for Q&A and discussion. So again, please state your questions in the chat so we can discuss them. And then I would like to give the floor to Vincent Voet, Associate Lecturer at the NHL Stenden. So take the floor, Vincent.
Thank you very much, Wilhelmine. I will try to share my presentation. Which should be visible right now. All right. Thank you, Wilhelmine, for your nice introduction. I'm indeed working at NHL Stenden University, which is an applied university. And before we start, maybe good to add a few words about my organization. It's a multi-campus applied university. We have students all over the world, from Asia and Africa and the Middle East to the Netherlands. Most students are studying in the Netherlands, and particularly in the northern part of the Netherlands. And the technology department where I'm working for is situated in in Emmen and in Leeuwarden. I'm working at the Professorship Sustainable Polymers, which is doing research together with industrial partners and, of course, our students on biopolymers, 3D printing, recycling of plastics, biocomposites for constructive applications, also sustainable fibers that we can use in biocomposites, and other topics that all relate to circular and bio-based economy. And today we'll focus mainly on our biopolymer research. So Wilhelmine showed already a beautiful picture of our unique ecosystem in the northern part of the Netherlands. So I will not spend too many words on this. I think it's important to remind that we always work together with companies, mostly SMEs, and other knowledge institutions, of course, and our students. So let's have a look at a more global view. This is data from the Ellen MacArthur Foundation from the year 2018, but the numbers are still pretty actual. 78 million tons of plastics are produced every year for plastic packaging only. And as we can see, the material flows are largely linear. So about 40% ends up in landfills, even worse, more than 30% ends up in the ocean. About 15% is incinerated, and the same amount is collected for recycling, and even less is recycled actually in a closed loop system. In the Netherlands, we're doing luckily a lot better. About 25 to 30% of the plastics are recycled nowadays, depending on whom you believe. but still we have a lot of work to do. And according to the Ellen MacArthur Foundation, we should reuse, reduce, and eventually also recycle our materials to improve. And in addition, most of plastics are nowadays made from crude oil, and therefore we should also decouple plastics from those fossil feedstocks. Bioplastics play a role in both of these topics, and yeah, you'll find out hopefully today. I always like to show this this picture also to our students, and today to you. This is maybe some of you know it already. It's a closed-loop economy model or circular economy model, again from the Ellen MacArthur Foundation, and it's showing two loops or two cycles: a green biological cycle and a technical cycle. So the blue technical cycle is about reusing, remanufacturing, refurbishing, and if needed, recycling of materials. And in our case, we discuss plastics today. And the green circle is about taking materials from nature. We call them natural or renewable resources to make bio-based materials, such as bio-based plastics. And if possible, we could also give them back to nature again, in case they're biodegradable, and they could be, for example, degraded by microbes. And if not possible, they at least should enter the blue cycle again, where they can be recycled. So important to understand that, yeah, we strive towards this circular economy model also in the Netherlands. And our research groups, both in Leeuwarden and Emmen, try to contribute to this, this system. To understand plastics, we should know a little bit about their behavior. So I think it's important to understand that there are two main types of polymers. For those of you who not yet know, we have thermoplastics and thermosets, and I would like to show you some examples of both. And we start with thermoplastic polymers. Thermoplastics are intrinsically recyclable materials. Most bioplastics are also thermoplastics, and in general, 90% of all plastic materials are thermoplastics. Then if we consider bioplastics, there are three main types that we should mention today in this webinar, I think. First of all, we have bio-based bioplastics, and those are materials that are made from biomass and renewable resources, such as corn, sugar, or cellulose, starch, these type of biomass. And I think a beautiful example is bio-based polyethylene that is used nowadays by Lego to make their little trees and plants. But also the plant bottle used by Coca-Cola and Heinz company, partly bio-based polyester. And also a nice example to mention today, I think, is a beautiful example of our good collaboration here in the northern part of the Netherlands. You see the companies stated on the slide who together made 100% bio-based polyester here in the northern Netherlands. The second type, I think it's worthwhile to mention, is the degradable plastics. So they are still fossil-based, but degradable, like PBAT and PCL. You see an example of a biodegradable plastic bag over here. And we have a third type of bioplastics, which are both bio-based and biodegradable. We'll see an example in the presentation of Bart Labrie later on from HMP Molding of it's a really nice example of a biodegradable coffee cup made from PHA, but he will tell you more about it, I believe. And yeah, maybe the most famous bioplastic of all is PLA, polylactic acid, or sometimes referred to as polylactide, which is nowadays used in the 3D printing market, for instance, but also in the packaging market quite often. And it is bio-based, or can be made bio-based, and also biodegradable, or to be more specific, biocompostable. So it's important if we want to state whether something is bio-based or biodegradable, that we understand certain standards and certain tests that have to be done before products can get a certain certification. So we see all type of logos over here. It can be a little bit confusing nowadays because there are several institutes that give all types of certificates. On the left side, you see some certificates for bio-based plastics. For example, those from TÜV Institute from Austria and Belgium, or Dinge Prüf from Germany, and the 100% bio-based logo here in the Netherlands. And on the right side, you see some biodegradable certificates. And here you can also see that I was hinting to this when I was mentioning PLA in the previous slide, that biodegradability is really broad term. For example, some products are biodegradable in water or in marine environments, while others can be degradable in our own soil. Thermoplastic starch, for instance, is degradable in home compost systems, while PLA is only degradable in industrial composting plants. So yeah, it's important to understand that this is quite a broad category of plastics. Let's have a look at the global markets. Here's your answer to the question of Willemien. Circa, but actually to be precise, less than 1% of the total global production capacity of plastics is bioplastics nowadays. The market is growing, as is the complete market of plastics, by the way. It's going slowly, but steadily. And if we have a closer look at the different markets for bioplastics, we can see that packaging is the largest market segment for bioplastics, which is also the case for fossil-based plastics, by the way. But we also see textiles, for instance, the PTT carpets that are abundant over there, and agriculture, which is an important market segment for the biodegradables. So what are we? What type of? So you can see there's still a lot of work to do, and therefore we work together with our partners and our students on several research topics. And one I would like to mention today briefly is the synthesis and recycling of polymers, biopolymers in particular. So recently we built up a new polycondensation, lab-scale polycondensation reactor in our lab that is able to produce and synthesize custom-made polyesters. And since we start from the building blocks ourselves in this reactor, we can make custom-made polyesters with different types of biomass, and therefore we can tune the properties of the material. And we do this together with companies such as Croda and Sembis Polymer Innovations here in Emmen. And on the other hand, we have a lab-scale reactor that can be used to do the reverse process, namely depolymerization of polymer products. So in fact, we can take the polymers that we make in our reactor on the left side, or we can take polyester feedstock from textiles or other plastic products and depolymerize them via a process called chemical recycling or molecular recycling, and see whether we can actually recycle this material towards valuable building blocks. And this is somehow a circular system in that respect, that again we can take the building blocks, polymerize them, degrade them, etc., etc. But these are typical products that we do together with industry. Okay, to conclude, because there are other speakers today as well, I would like to say a few words about Thermoset polymers. Thermoset polymers are intrinsically not recyclable, at least the traditional ones, because of their cross-linked nature. For example, a famous example are the wind turbine blades or car tires, for instance. And we have to find some solution for this. Yeah, an important market nowadays, an upcoming market for thermosets is that of additive manufacturing. And it's a new technique that is used to build custom-made products. However, the 3D printing inks that are available right now at the market are all fossil-based. And together with Licreate and the University of Groningen, we try to develop bio-based inks for 3D printing. a very prestigious project. And in recent years, we were able to produce 3D printing inks based on soybean oil, and lately even cashew nut shell liquids, or cardinal in other words. And in this way, we could print with bio-based photopolymers to make bio-based thermosets. So to give you an idea, maybe some of you have never seen this type of 3D printers that create thermosets. So I have a small video to show you the idea. So to explain what you're seeing, you see a liquid bath of photopolymers. They are light sensitive, and a laser is curing the light sensitive photopolymer into a solid thermoset, layer by layer. The product that is formed is hanging on top of the black lid. So the process is upside down, actually. And in this way, you can build layer by layer a three-dimensional construct. Okay, so that's nice. We are able to create bio-based thermosets via 3D printing. It's a good step forward, but still the end product is not recyclable. So how to solve this issue? And this is a new research project that is running at our university, where we try to use a concept that was created in academics about 10 years ago, which is using bond exchange reactions to create a dynamic network or a reversible network in such a way that thermosets can be recycled. Okay, that's quite technological. So if you want to get more details, you can contact me later on. But for now, those products are called Phytramers, and we try to implement this Phytramers into the 3D printing technology. And this can be very interesting for markets such as automotives and yacht building. Okay, I hope to give you a small impression of the world of bioplastics. I'm sure that Jan Willem and Bart later on will give you an even broader perspective. For now, I would say back to Willemien.
Yes. Oh. Yes, thank you very much, Vincent. Very interesting research you are doing at the NHL, Stenden. And looking forward to what the future will bring with all the projects you have. So, very interesting. Thank you.
Thank you.
Then Jan Willem, I'd like to introduce you to share your screen and tell us more about what you do at SEORG and the developments you see with bio-based polymers, and also, of course, the markets in which you operate.
Yeah, thank you, Willemien. My name is Jan Willem Slijkhoort, and I'm the owner of SEORG. It's a Gaelic word for.
Can you share your presentation?
Yeah, I thought I had, but
F5.
Sorry, F5.
Yeah.
No.
Or at the bottom of your presentation.
Yeah.
Hang
on.
Yes.
Here we are. Thank you. So, welcome everybody. Although we speak each other virtually, it's glad to have you here all. Thank you, Willemien, for the introduction. My name is Jan Willem Slijkhoort, and I'm the founder of SEORG. It's a Gaelic word and derived from the Gaelic word circle, which means circle. So that's why it is SEORG. And I would like to talk to you about the bio-based and soil degradable polymers, which are capable for 3D printing applications and even more. But at first, let me introduce myself. What is SEORG, and what are we doing basically? It's a clean tech up, which I've started early 2015. And we are active basically in the chemical recycling technology of specific plastics and textiles. We started our activities in sustainable polymers suitable for 3D printing. And I first started it by developing recycled materials based on hospital waste. And we turned that into 100% recycled PET material, which is food compliant in both PET filament for desktop FDM printers and granulate for large robot arm printers. Since 2 years, we are also developing bio-based and soil and water degradable polymers suitable for 3D printing purposes. Because this is a group of polymers which are not frequently used for 3D printing purposes yet. And they have interesting properties compared to PLA. So I will talk you to that later. But our main drive is mainly to make something out of almost nothing. And so we focus to develop high added value circular businesses based on material technology. Something about myself, I'm 52 years old and graduated in Material Sciences, Technical University Delft in 1994. So I've experiences in material sciences, not only polymers, but metal and metal alloys as well, and business development since over 25 years now. And I use this kind of experience and network in the industry and knowledge institutes and laboratories to develop new circular businesses. Just to give you an example of which I started, in 2014 I came into contact with people with had waste and would like to upcycle it. On the left side, you see the PET polymer waste trace, which is widely available in hospitals. So we pick it up and we managed to upcycle it into a very pure PET polymer via mechanical recycling, and to upcycle it with similar properties like the original virgin packaging. And based on that, we have modified the materials somewhat in order to improve the printing performance on 3D printers. At first with filaments, a kind of thick thread, so to say, which is dosed into a desktop printer and enables people to manufacture small items on the desk, like you see here, a prosthesis made from inner circle. So, but that hasn't to do anything, of course, with bio-based, as you can imagine. But it was a start for us to get acquainted with the 3D printing market, the needs, and also the issues which plays a role, because 3D printing is a magnificent processing technology, but completely different than extrusion or injection molding like HP molding is doing. Okay, so currently we got interested in developing more bio-based polymers except PLA, because PLA is the working horse already in 3D printing. There's only, from biodegradable point of view, a disadvantage that PLA is biodegradable, but only biodegradable in industrial composters. So this means that the biodegradability is limited, to the industrial composters, so home composters or marine degradability or soil degradability is not the best point of the strongest point for PLA, so to say. We noticed that more and more interest is gained from customized products which are fully biodegradable in natural waters and in soil. So we started to do some tests. And right here, we started first our own test about the biodegradability of several biopolymers, which we exposed into soil, which is enriched with microorganisms. The microorganisms is an important addition important condition for the biodegradability of different biopolymers. And on the top left, there you see 3 different types of biopolymers. And due to reasons of continuing research, I'm not able yet to express what is the exact type of biopolymer compound. But right here you see 3 different compounds, as you can see at the start, 0 weeks, completely fresh. And we expose them into soil, which is enriched with microorganisms, both outside and inside our company. And you see that the middle and the right type of biopolymer compounds is clearly degraded, and the left one is fairly undegraded. So you see, in about 12 weeks, 3 months, so to say, we noticed that depending of the type of biopolymer compound, there is a significant difference in the biodegradability in soils in this case. So you see that biodegradability is very dependent on what environment it is exposed to, under what conditions it is. Is it aerated or not? Are the right microorganism developing which can attack the polymer and convert it into carbon dioxide and water? So convert it in a way that no harmless substances remain behind after the degradation. Furthermore, so we have selected a number of interesting compounds that are able to degrade in soil under several conditions, of course we want to print it, as you can imagine. And I can tell you that's quite a challenge, because a lot of biopolymers, except PLA, they have the tendency to warp, and warping means that there is a strong or lesser deviation towards the desired dimensions of the product that you want to print. And if the material warps, then you have basically not the right sizing of the intended product. So you want to avoid warping in any case. And most bio-based polymers, which are also biodegradable in soil and natural waters, they warp a lot. So we had to modify those compounds such that the warping is counteracted. And right here, I would like to see you an example of the printing. This is a bio-based compounds with cellulose fibers. That's why it is brownish. It's a short movie, I will repeat. And you see a good flow and also a very stable buildup of the of the test sample. And this is in our accordance a very strong and a very well printable material, which doesn't warp anymore. So based on this, we would like to develop new type of bio-based and customized and printable materials. And we also think that this type of compounds could also create materials suitable for injection molding. Yeah? So suitable for Bartleby of HB molding, which we will explain later on. So we talk about, of course, high added value applications, because that's the main driver for material development, of course. And I have a vision that currently, like explained by Mr. Vincent Voet before, you see that most of the bio-based and biodegradable polymers are applied in packaging. Packaging is mostly used once in our society still. So if we want to have high added value applications, by the way, application is also highly valuable, but which we can use again and again, then we have to take into account consumer products which are made of engineering plastics today as well. So if you have a look at the left corner under, there you see housing power tools, which are currently made of nylon 6 with 30% glass-filled fiber. It is possible to modify bio-based and biodegradable materials based on cellulose instead of using the nylon 6 with 30% glass fiber fill. And this could give the power tool makers an sustainability advantage, because that material can be degraded and doesn't need to be recycled, which is also very difficult for the nylon 6 with 30% glass fiber fill. You can also use it for bedpans, because in hospitals and care houses, bedpans, of course, are frequently used for elderly people or patients which have manure in it. So you can throw it away, the bio-based and biodegradable material with the manure without any problem. In the middle, the biodegradable well plates, currently made of, for example, polypropylene, but frequently used and frequently and quickly disposed. So if you want to improve as a hospital your footprint in the laboratory, then the use of biodegradable and bio-based well plates could be very, very helpful.
And Willem,
as you can
you
imagine, on the right-hand side under, you see soil degradable 3D printing pots. This is a typical example of outdoor applications for consumers who want to pay a premium for customized design. So, and also right there, bio-based and biodegradable material, soil degradable materials can be very beneficial. And these are a number of examples which are both, I think, high-tech and give you a high margin product opportunity. So, so this is what I would like to share with you about bio-based and biodegradable materials for 3D printing. I would like to thank you very much for your attention, and I look forward to answer any of your questions or remarks. Thank you.
Thank you very much, Jan Willem, for your presentation. Also very interesting development. So let's see what Bart Laprie also has to add on that printing of injection molding of the materials you also print with. Bart, welcome.
Thank you.
please tell us a bit more about your company and the developments you've been working on with bio-based polymers.
Okay, as the other people already said, I'm working for H&P Molding. I'm the CEO there. Next to that is I'm also chairman of the SUSPEC organization, a cluster of sustainable products and chemicals companies in the Emmen region. And as the word says, they work all on sustainable materials and plastics. H&P Molding, going to the next slide, is a producer.
Bart, we cannot see your screen yet, so please share your screen.
Oh, sorry. I thought I shared it already. I do apologize.
Not a problem.
It should be this one. Share. You are screen sharing. Yeah? Can you see it, Willemien?
Yes, we can see it. Thank you.
Okay. Sorry for the mix up. So you can see the type of products we are producing currently. It's all technical products. One product you may recognize, that's the spuittuit for the Vechter, which is going to be bought by everyone around Christmas and New Year's Eve. Further on, we produce products for the medical industry as well as for the food industry and the technical industry. As Vincent already said and mentioned, there's quite a high level of plastics, high consumption of plastics in the world, around about 400 million tons in total, of which packaging is taking the largest part, but also the electronics, the car industry, transportation and others are quite strong still. And if you then compare it to the global capacity of bioplastics, that's only 2.42 million tons. So that is really far less than 1%. And this makes it already a niche product in itself, as Jan Willem also mentioned. So we have to keep in mind that, yes, we are talking about bioplastics. Yes, we think it's going to be the future for everything, but at the moment, it's only far less than 1%. And the growth is also not extremely high. The growth is quite strong in Europe. And that of course, has to do with the regulations which are now going to be in place. The climate aspect is of course heavily impacting the use of other types of materials next to recycling, also the biopolymers and the biodegradable polymers. And of course, the pollution of the sea is certainly one of the issues which we are seeing. So that is one of the reasons why bioplastics is certainly in Europe growing. That's one we saw already. The next slide is a little bit about further explanation of bio-based plastics versus the oil-based plastics. That the energy requirement is lower for bio-based, as well as the global warming contribution is lower. So that helps the bioplastics to gain a position in the world and in the industry of plastic products. If you then look at the performance, the mechanical performances of bioplastics, there we see that PHB or PHA is doing quite well. It's comparable to epoxy. And as Jan Willem already mentioned, if you may add some fibers to the PHA, it may grow up to the PHA. PLA is also very well known, especially in the packaging industry, comparable to polystyrene. And then in the other areas, you have the PBS and the PCL. If you look at it on itself, the performance of bioplastics is certainly not outstanding compared to the current plastics. So their behavior, their performance is relatively normal. So what is the benefit of bioplastics? Well, one of the things we have to see is that next to the normal use, is basically a post-mortem. They are degradable. They are giving you a lower carbon footprint and a lower contribution to global warming. It's not something you see when you buy a plastic product, but it's something which happens after its life at the consumer or at the customer. So what you basically can say is that bioplastics are far more the memento mori than the carpe diem. Enjoy the day is for the current plastics, but the bioplastics certainly are having benefits, and you can say that basically they're materials from heaven. Their value added is to a larger part also after their life, the current life. If we then look at the bio-based polymers, you see that yeah, the material costs at the moment are higher. Are they going down? Probably yes. Are they going to reach the level of oil-based materials? Doubtful. The processing costs, as we currently experience, are higher, so it's a longer time to produce. That means that the customer's price is higher than comparable products in oil-based plastics. But at the end, the society costs are going to be lower, especially because of the disposal costs, which are now not being added to the price the customer is paying, but is something society is paying. So there should be a benefit there. Coming back to the main headline is the high value markets. Well, we think that if you make products by injection molding and you go to the markets with the high value added, you make them sustainable and high price, there is certainly a market for bioplastics. And if you then look at the technology revolution, which is ongoing in the world, and you start looking at, okay, suppose that as from 2025, the bioplastics are going to gain a more stronger position. And then bioplastics, for instance, like PHA, PLA is of course already longer in the market. And you can see, okay, what markets do we want to go in? Where are the high value markets going to be? And this is something which could help you. One could say maybe in the aircraft industry, maybe in electric cars, there are opportunities. Maybe in electronics there are opportunities, and also maybe in medicine and genetics there are opportunities. And especially I want to focus a little bit on that last part. So I don't think that these kind of disposable food trays, which you can find at the Big M, are going to be the real market for these relatively expensive bioplastic materials. One could think maybe a water bottle is going to be something else, a niche water bottle, not the most common ones which are going to use, which are using PET, but other ones, a niche market. It could be something like that. If you then look at what HMP molding is doing, it certainly is for instance, in coffee cups, which we're doing together with a customer, limb recycling, and we're trying to see what is the market, what are the opportunities, how does a product behave? Because if you use these kind of products at festivals, like the water bottle, maybe you can collect them, but if you can't collect them, they're going to be disposed of in a number of weeks, and the area is clean again. Coming to the medical products, because in the medical market there is what we consider it's relatively high value, and at the same time it's also producing a lot of waste. The main thing of the medical industry is, of course, it has to be better safe than sorry. It has to be absolutely clean and no source of infection for patients. If you then look at for instance, the Canadian hospital waste composition, you see that plastics is taking 14% of the amount of waste, which is not as much as paper, but paper is more easily to burn and to dispose of. Plastics is certainly still a significant part, where something is to be gained. especially since a lot of products are disposable. So for instance, what kind of healthcare products are you then thinking of? For instance, all trays which are being used in laboratories to examine the blood or the urine or any other of the body liquids. But also you could think of ventilation machines and other medical devices, disposables, etc., which are packaging also, which is being used which you can use for biomaterials. However, there is of course a requirement to healthcare products, and that is the medical grade. If you want to produce a medical product in plastics, it has to be a medical grade. That is one of the things which is very important to anyone. And as you can see by a statement of Dr. Katharina Neumann from Raumedic, the watchword is consistency, and that is certainly one of the issues that is at the moment still difficult to achieve with biopolymers. The consistency is not yet there, and that is something we have to work on. Another aspect is that there are quite a number of stringent requirements. For instance, the medical device regulation in Europe, the FDA in the USA, the ISO 10993, which indicates, okay, you can use, if you want to use it in the body or outside the body or whatever, there are specific requirements. So that makes it more difficult and certainly not a short-term possibility to introduce a medical products. But at the same time, we do need to work on it because we still have that 14% of hospital waste, which is plastics. So summing up, what is then required, what is needed for bio-based polymers to enter that high value market? Customers and consumers, they are extremely important. If you don't have a customer, you can push the product and the technology, but it won't work. So we need customers and consumers, and they need to be convinced that it's something interesting. So is there a way for them? Of course, the governments and legislation can play and should play a strong role in getting these materials accepted, facilitating the legislation. And at the same time, of course, also governments could play a role as a launching customer. We need to do, and we are doing that with the Knowledge Institute, like NHL Stenden and like the Groningen University, the research and development. Can we make the materials better? Can we make them more suitable for more processes, etc.? And in the end, yeah, curiosity and courage, that is something we need. And we have to show, are you curious enough to start using a biopolymer, and do you have the courage to start to put it into a product and to apply it in wherever you want? So basically one could say plastics, yeah, we need to reduce plastics, and it's certainly also in the medical area. It needs to be better safe than sorry. Now, if we marry those two, we think you can get a medical grade, which is biodegradable plastic product. And that's the end of my presentation. So, and I would like to thank you, and I hope I made it within the time.
Good enough. Good enough. Thank you very much, Bart. Thank you all our speakers. I would like to continue to the discussion. One of the points you also mentioned, Bart, is that we need customers, we need consumers to increase the demand, of course, for these bio-based polymers, biodegradable or not biodegradable. We need an increase in demand to increase, of course, production capacity. It's a chicken and the egg discussion, perhaps as well. But you work in these industries, in the healthcare industry, in the food and technical industry. Do you also see an interest in these, in your clients, in these type of polymers?
Yes, we certainly see an interest, a growing interest in these type of polymers. At the same time, there's also the reservation of the fear that the material is not good enough for the application. If you start discussions with customers around oil-based polymers, and you say, okay, we recommend you to use, for instance, a polyamide, a nylon, then they say, okay, yes, looks good, yeah, fine, okay, if we can do that, it's a medical grade, yes, there's no further discussion. If we start the same discussion for a product and you say, okay, well, we would like to introduce a PHA in whatever format, then we get far more questions than we can answer, and then you, yeah, it involves everything on carbon footprint, performance. Is it biodegradable? Does that mean that when it's being used in my application, that it degrades? Sometimes it does, but most of the cases it doesn't. And that's the kind of, I would also say the curiosity and the courage of customers to start going to use it in these in their product.
Yeah, fair point. I see we have a question, so I'd like to state that. This is from Stefan van Halle of Stax NV. Would a perfect circular solution regranulate the plastic and manufacture the same device? Oh, not be a solution as good as a biodegradable plastic? So I don't know if someone has an answer for that, or we can use this later. Vincent, you're muted still.
Yes. Can you repeat the question, Willemien?
Yeah. Would a perfect circular solution regranulate the plastic and manufacture the same device, not be a solution as good as a biodegradable plastic? So the discussion on recycling versus biodegradability.
Yes. It completely depends on the material and the application. So if we go back to the model I was showing you of Ellen MacArthur, of the two-cycle system, they're both are in there. So in the green cycle we have the biodegradables that can be given back to nature, and will be valuable feedstock later on for new bio-based materials. But sometimes it's definitely much better to recycle the material, and it will have a lower cost, lower economic cost, but also in terms of sustainability for the environment, to recycle the product. So it depends. There's not, I always say there's not one solution for this plastic problem, let's say.
Yeah.
So definitely in some cases that's true.
Yeah.
Yeah, I would like to add to what Vincent says. Indeed, there's a market for biodegradable products, definitely in the market in the world, but also to recycling materials. One thing we should not forget is that if you recycle plastics, it loses performance, and you can upgrade it. There's a lot of development going on to upgrade materials to make it to the same performance. But of course, that means that you add energy to it. And if you then look at not only the degradability, but also the energy consumption of materials, it makes the whole balance and the whole picture even more complicated.
Yeah. Okay. I have a question here from Jesse Dolstra. I don't see the organization's name, but it's for all speakers. What are the biggest challenges in establishing a higher level of consistency in bio-based polymers?
I can say something. Of the first question that popped up into my mind, that was consistency in what? Mr. Dolstra didn't make explicit what he meant with consistency. If you talk about consistency in properties, then there is a big challenge in making bio-based biodegradable fibers with comparable properties like PET. And that has to do with the consistency in the polymer chain length. So the longer the polymer chains, the better the properties. If you compare a PHA or PHBV or PBS and even PLA with PET, then the properties of PET fiber are significantly higher in terms of strength and elongation compared to the bio-based biodegradable materials. And for example, you would like to be this type of development solved because if you talk about fleece jackets and you wash them, there are a lot of microfibers occur after a laundry cycle. And if fiber breakage after a laundry cycle occurs with biodegradable, marine degradable materials, then that would not harm the environment to the same extent like PET fleece jackets do.
Okay.
And maybe in addition to Jan Willem, a quick statement, we should also not forget that some bio-based polymers are drop-in chemicals. So bio-based PE is made from, for example, from sugars, but the PE is when we produce ethylene, the monomer, and we polymerize it to polyethylene, it is the same polymer as polyethylene from crude oil. So for some bio-based polymers that are drop-ins, there is no difference in the end.
Okay, thank you, Vincent. I think we have reached the time limit of 5 p.m. So I think I don't see any other questions. One was already a bit answered. So it's not a very elaborate discussion, but I would like to invite everybody who has been watching and listening to this webinar. I'll share my screen. To stay connected with Chemport Connect. This was one of the webinars that we have been hosting. There will be a few more webinars also on the 28th of October. I'll be moderating one about European developments towards biodegradable polymers. So that's also a connection with this webinar with a few very interesting speakers. November the 14th is also more on the feedstock for sustainable plastics, and November 11th on developing a future-proof circular plastic system with the National Test Center Circular Polymers, and leading up to a digital event on the 17th of November. And all these webinars are being recorded. So if you join our community, you can continue the discussion on the community and also look back all the webinars we've been hosting. And on the 17th of November, we have a large digital event. So I would like to thank our speakers a lot for sharing their knowledge. I hope that you as viewers have gained new knowledge, new insights on bio-based polymers, applications, new technologies like 3D printing with thermosets, and also developments with recycling of these materials, injection molding of bio-based PEJ. There's a lot going on. So please stay connected, stay tuned. Thank you for watching, and hope to see you again, and stay connected. Thank you all, and thank you for participating, and
bye-bye.
Good.
Okay, thank you.
Bye-bye.
Bye.
Weet je, ja, ik denk de tijd is nu op.